Hello, my name is Lauren Mack, and this is my analysis of Lab 3, Black Holes and Orbits. The purpose of this lab is to calculate the mass of a black hole using the given distance, the mass, and the period of a nearby star. And in part 2, I attempt to estimate the velocity of a ship that would keep it in orbit around a planet while the planet, when I say planet, I mean moon, while the moon is in orbit around another planet. The computational model shows that the varying values for the mass of a black hole as the planet completes its orbit, and the model in part 2 demonstrates that the perfect orbit might not be possible due to varying speeds during multiple different orbits. In this lab, we see a continuation of Newton's second law, which states that F net equals the change in p over the change in t. We can change this into an instantaneous value, which signifies the change in speed as the change in magnitude of momentum times the direction, which is unchanging, and the change in direction as the magnitude is unchanging. But in this case, and on another equation that we're using is the universal law of gravitation, which signifies that there's an attractive force between two objects, which is why it's always negative, and the equation relies on the square of the distance between the two objects, more specifically the difference between the position of the system and the position of the source. So in part 1, we had the initial conditions of the constant of gravity. We also had the mass of the star and the change in time in seconds, which is 1 day, and the initial time, which was 0 seconds. When we were calculating the change in net force, we needed to change the momentum, or calculate the change in momentum, which is seen in Newton's second law in order to find the change in instantaneous momentum. We then calculated the change in direction versus the change in magnitude of the components, and we used them to calculate F net parallel and F net perpendicular. We then took the values of the magnitude of F net, then we plugged them into a gravitational equation, and we organized it to get the mass of the black hole as seen here. So the final results show these values for F net, F parallel, and the mass of the black hole. Finally, these were the final values, but they stayed within the range of 1.48 for the mass, times 10 to the 34th. And the initial conditions for part 2 include the mass, the gravitational constant again, the mass of the planet, the mass of the moon, the mass of the ship, the change in time in seconds, which was 90 seconds, and the time 0, which is the initial time, and the T max, which I changed from 700 to 2001 because 700 only made it 1/3 of the way through the actual orbit. So in this experiment, what we did was we found the distance between the planet and the moon in order to find the force of the planet on the moon. Then we did so for the ship as well as the ship on the planet and the force of the ship on the moon. The directions of the distance are what was the major difference between the forces, and then we plug these forces into F net in order to find the velocity of the moon and the velocity of the ship. So in the final results, I couldn't manage to get a perfect orbit without the moon and the ship crashing due to the change in speeds, as both of these objects orbited around the planet as the speeds of the moon decreased as it got farther away from the planet, and it allowed the speed of the ship to decrease as well, as you can see by the increasingly longer period as the ship and the moon continue their orbit. The velocity I chose was negative 25 meters per second in the x direction, 50 in the y direction, and 0 in the z direction, which was the point where the longest orbit occurred. So some possible errors that occurred were inaccurate estimations when it comes to part 2 of the lab, implying that there is a closer speed to a full orbit that I might have overlooked, and when calculating the mass of the black hole in the first part of the lab, there could have been inaccuracies when rounding, leading to less accurate measurements. So here are some questions to look at. How are the components of F net different from the components of the rate of change in momentum? To that, I would say that there is no significant difference, but the momentum is purely a change of momentum, signifying the change in speed and the change in direction of momentum, while it does not factor in all of the forces that could be acting on an object at any given point in time. To the second question, which is, if you want to predict the motion of an entire system, what would you need to include for your computational model? Well, what you would need to do, since there are multiple objects in our system, we can use energy equations using potential energy because it's a multi-particle equation to calculate the initial velocity between the relationships between kinetic and potential energy at any point in the bound system. At any point, some parts would dominate because some parts would always be closer to others, leading to a larger gravitational potential energy and less a larger speed at some points, as well as a larger speed at some points, which would ultimately lead to some forces having more attractive potential than others. In conclusion, I saw that this lab was hard to create a perfect orbit, and that varying masses of a black hole show that that mass is relative to position. Thank you.